intensity coming from the area A1 multiplied by d lambda multiplied by the solid angle subtended by the area A2 as seen by the observer A1. I'm going to call it as d omega 1 2 multiplied by the portion of the area A1 that is seen by the observer sitting at A2. So that's going to be A1 times cosine theta. Does this make sense to everybody? You see the various quantities. This is the intensity coming from the area A1. This is the fraction of the wavelength range I'm interested in, and I'll be integrating over this entire wavelength range. This is the solid angle subtended by the area A2 as seen by an observer at A1. Okay, so if I draw it out here, this is the angle d omega I'm talking about. And the last one is the most important one here. This is the fraction of the area that's emitting the radiation as seen by an observer who's sitting at A2. Okay, this is what we had from the previous problems and previous situations as well. The only thing we need to calculate is d omega. Last couple of minutes. And because you are told that, okay, hey, I'm looking at only radiant energy over a small portion, I'm not looking at radiant energy over the entire hemispherical bulb, I don't need to integrate over the directions. This is only for a small fraction of the area that I'm looking at, not for the entire hemispherical bulb. So dq12 I lambda comma e is independent of theta and phi because it's coming from the diffuse emitter. So this is just lambda comma e lambda. D lambda still there. D omega 1 2, watch this. I'm not going to bring in the sine theta, d theta, d phi because I'm not integrating over the range of theta and phi. My area A2 is a small portion of the hemisphere. So this is just going to be the definition of the solid angle. The area A2 divided by the square of the radius from 1 to 2. So that's this distance essentially. And then A1 times cosine theta. Where theta is 60 degrees. I divide everything by A2 so that I get dq12 double prime, which is dq12 by A2. This is I lambda comma E d lambda. And then A1 cosine theta by R12 square. This is just a fraction over the wavelength range d lambda. If I want it over the entire wavelength range from 0 to infinity, I just integrate from 0 to infinity for d lambda. That's also from 0 to infinity, 0 to infinity of d lambda. This is the net radiative flux that is received by the surface A2. And the very last line for the day. So Q double prime 1 2, which is 0 to infinity dq 1 2 double prime, or integrated over the wavelength. Okay, this is essentially I lambda e 0 to infinity multiplied by A1 cosine 60. The distance 10 to the power minus 2 times 50 whole square. This is a radius from 1 to 2. Area A1 is given to me 10 to the power minus 4 square, 10 to the power minus 4. This is a square area, let's say. That integral is nothing but IE substitute, obtain the integration. Alright. So next class, we're going to start looking at an ideal body and then look at Max Planck's theory and how that applies to the study of radiant energy. Okay?